还可以试着学习到的东西在里面。那其实还算一口气也是日本的，他们说好像现在对点点点。Oh,
this one. So make sure this one is red.
We want to change the tab.
Wait, huh?
We want to change to another slide. We change to the another tab. Is in
yeah. You can full screen. You know how to do full screen?
Where was it? Full screen?
Why is it not? Yeah, about the but this one not here. 3次以前 used to be able to do that. How about screen? Do screen. Why cannot? How about I think I know how to do it. Okay. So we start first pull this to the other side instead.
Yeah.
Then this one here.
And share this one.
This one.
Yeah.
It's like that.
Yeah, I think we now share slide.
Yeah, it's not showing. Yeah, then how? We just like this.
Maybe you
Good.
you maybe go here.
Or duplicate. Using duplicate. Okay.
Yeah,
Makes sense. Yeah, so duplicate. Okay, after duplicate, open again. Okay. Better. So make sure this is red when you're recording.
Usually, okay.
Yeah. Later, can you help make sure your group?
Okay. Then change. Maybe I set up this first.
Yeah.
And full screen is what now?
Full screen is somewhere here.
Okay. It's a bit hard to change.
Yeah.
Yeah, we to change text.
Change what?
Change text. Because I can. Oh, yeah.
Maybe you can make it smaller first.
Okay.
Or you just, you just, after finish one, you just maybe can delete it.
I think that works. Okay. No.
Hello, testing 1 2. Hey, where's the other group? A member? Where's the other group? 问一下 member 那里，叫他们来。Okay. So before we start, so each member will be given 20 minutes. Okay, at most 20 minutes. So I think later we will have a timekeeper. Lydia will be our timekeeper later. Yeah, I got a bell. Okay, so 17 minutes we will signal you. You have 3 minutes left. If you want to finish at about a bit more than 15 is okay. Yeah. So if your time not enough, we also tell you haven't finished yet. 15 minutes. So 17 minutes will signal you to finish, and then 20 minutes you must finish no matter where you start. Yeah, because we need to keep the time. And so we could have 5 minutes for personal question if there is. If there's no, then we will proceed to the group Q&A. Okay. The idea here is make sure you get asked. Otherwise, I cannot see how you perform. Okay. Yeah. Whether answer right or not doesn't matter, but the point is to see how you're thinking. Okay, how you react. how you answer. I think, should we turn off the light? I think this is okay, right? Can see, right? Yeah, sure. Okay. Yeah, anything else? Yeah, I think later, before finish, I think we should take a group photo, and then when more people come, I think preferably before lunch, because some of you have to leave after lunch, and try to take a group photo for each group after finish. OK， 有叫你们 member 来吗？要不，那组长都没有来，来不叫他来不？9L 呢？我看到他组就你们放 slide 上去了，就他放 slide 上去。OK， it's OK， 能叫哪个把我们叫过来。Okay, so now we have a group from Vice, okay, to talk about Toric variety. So there are 5 topics they cover, right? What are the topics? You want you to use this? Yeah.
Then talk about homogeneous reporting, and that is after that. And then we continue with homology for Toric variety, and last my part is the resolution of singularities for Toric variety. So let us begin with our first speaker, Lin Chin.
Okay, thank you. So, good morning, everyone. My name is Yo Eugene, MNT 2309135. So, as you can see, today I will gonna have an introductions to the Toric variety. So, okay, as you see, you can see that we have a 32 page for me because there's a lot of definitions and theorems that I need to introduce for you. You can see that we have torus, affine toric variety, toric ideal, affine semigroup, convex toric hero cos advance, and also Gouring normal separate and separate of project toric variety, and the orbit coordinate coefficient theorem, and also the toric morphism. So before we start, I'd like to let you see about the notations that we didn't learn in our CAG classes. As you can see, for example, like T, which denoted as the torus, built by the torus, and also we have X, which is denoted as the projective toric variety also. Now it's okay for you to no need to remember all from now because later the presentation I will measure it one by one if I use it. Okay, so first of all, about the torus. Well, before the torus, I'd like to, there is a affine variety, C star n, which is a group of n dimensions under the component-wise multiplications of non-zero complex number. So, and then for the torus, we denote as T, which is affine variety that isomorphic to the C star n. So this is some example or picture of the torus. You can see the first one is the ring torus. The torus is how the torus view is that given a closed subset, I mean a closed curve, not closed curve, closed curve, and we rotate the closed curve around it. So we have a lot of different kind of the torus. And then next, move on to the affine toric variety. Well, we let the torus T n, which is T associate with the lattice n. N is as the set of all one parameter subgroup of T. And then the affine toric variety V, which is irreducible, and the Tn is subset of V such that the V is isomorphic to the C star n as a Zariski open subset. And then there is actions on Tn, which is the product of Tn and V sent to V. And then here are the example of the toric variety V. Let V as a V of X minus YZ, and then the intersection of V and the C star 3 is the set of T1, T2, and T1 multiplied by the inverse of T2, that the Ti is in C star. And then this set is isomorphism to C star 2, which you can see from here. And the next is about the toric idea. Well, let the set of lattice A is a subset of N, which is M is the lattice of the character lattice of a torus. And then YA is the affine toric variety of Y of A. So the definition of idea of the toric idea denoted as IYA such that the idea of YA is the generator of the difference between the x power of L plus and L minus. Well, the L plus and L minus, which the difference of them is L, which the L, the matrix A, the dot product of L is equal to 0. Okay, and here is the example of the idea, the toric idea. So we let the L as the tuple of L1, L2, which is 3 and -2. Sorry. And then for A, the dot product of AL is equal to 0. Then we take L plus, which means we choose the positive part of the L, and then the combination of them, which we get the 3, 0. And also for the L minus, which we take the negative part of the L and the combination of them, and we get a 0 and 2. And so we have the toric idea that's generated by x1 cubed, x2 0, which is from here, and then minus the x1 0 and x2 squared, and then it's form a generator of this. Okay, and then next we move on to affine semigroup. So let's set S which associative binary operation with the plus and the identity 0 as a semigroup. Then the affine semigroup generated by A, which denoted as NA, is the set of the combination of the M, which M is the element of A. Then NA is the subset of S, is finally generated. So here are the DFA statement, which the following are equivalent. If V is affine toric variety that defined by the toric idea, then if and only if for affine semigroup S, which V is the spectrum of the C algebra of S. And then also for finite set of lattice A, V is equals to YA, if both of them are also the affine toric variety. And then now let us move on to the second part of us, which is the convex polyhedral cons and the fence. So what is the cons? We denote cons as the sigma, which the sigma is subset of the n lattice, the vector space n R that generate the build from the n. Then the sigma is equals to the con of the S, which that is the combination of U. That U is a set of the semigroup. So here are the example of the cons. So above figure show the cons that we have 1, 2, 3, 4 cons, and four of the cons is also cannot as one cons. So for example, we have the cons tree, the sigma tree. The sigma tree is the set of x1 and x2, that the x1 and x2 is greater than or equal to 0. And that is also denoted as con. And also we have the sigma 1. Sigma 1 is also a con, that the con is generated, and the con is the set of x1 and 0, x1 0, which the x1 is greater than or equal to 0. And also sigma 2, which the x2 is greater than or equal to 0. And also we have the cons of 0, which is the sigma 0, that is only a point, and it is also denoted as a con. Okay, and then we have dual cons. Well, dual cons denote as the cons V, such that the cons V is the set of M that from the lattice from the vector space M that build from lattice M, and for every U that is in the con, the pairing of M and U is greater than or equal to 0. So the dual cons, which you state that how it works of the cons that the cons build. So, and also fun facts that for the dual of the dual con is you send back to the cons. Okay, and then for the semigroup algebra of cons, we denote as S sigma is the set of the lattice point S sigma such that the intersection of the duocons and the M, which is equal to X sigma. And by Gordon's lemma, X sigma is finitely generated. So there is a theorem that we let U sigma that is affine toric variety such that it is equal to the spectrum of CS sigma. And also from the previous definition of the semi-group algebra, the U sigma is equal to the spectrum of the C algebra of the intersection of duocons and M. And then there have TFAE statement which the dimension of the U sigma is equals to the dimension of the torus. And then the Tn is the torus of U sigma. And also the sigma is strongly convex polyhedron. Well, what is strongly convex polyhedron? So convex polyhedron, we use back to this picture. So the convex polyhedron, which means that the cons, the angle in between the cons is less than or equals to the 180 degree. And also strongly convex, strongly means that for two cons, we use the cos tree and also the negative of cos tree, which is the opposite side of the cos tree. And then the intersection of the both cons is only the sigma 0, which is the 0 points. Okay. And then we move on to the fence. So we denote them as the big sigma, which is the sum. And then the fence is denoted as the fence. It means that that is the finite collection of the strongly convex rational polyhedron. Well, for the rational polyhedron, which means that the vector that forms the cons is in the rational numbers. And then the fence should be satisfied the following property, which that for every cons in the fence, every face we denote face as a tau, and face of the cons is also known as the cons in fence. Well, we let two cons, con 1 and cons 2 that in the fence, then the intersection of the con 1 and cons 2 we form a tau, that the tau, which is the face, is the cons, both of the cons, which they share the same face. So this figure shows how what is the image of the fence. Which you can see that they have cons 1, cons 2, cons 3, and also the face. Face is also can be said as a cons. So we have the face that both intersections you share the same face. Okay. So by the way, the face of the con, this is an example of the face of the con. So we denote as we use the sigma 3 as a one con. Then the face contains sigma 2, sigma 1, and also the sigma 0. Which three of these cons is said it can be a face. But sigma 3 is not a face. And then there is a corollary. Every toric variety with torus Tn exists a fence that in NR, vector space NR. So the second final part, which is gluing and normal separate of projective toric variety and also the big cons corresponding theorem. So first about the gluing of collection of affine toric variety. So we left two cons, sigma 1 and sigma 2, such that the face of the cons is the intersection of them is share a face. Then the affine toric variety, which U sigma 1 and U sigma 2 are glued together with the subset of U tau, which is the face of the affine toric variety. So then about the normal of projective toric variety. If the projective variety is normal, then there is the projective variety X, such that for every P in X, if X is irreducible and also the logarithm of X and P is normal, then X is normal. Well, for the separate, if projective toric variety of X is separate, then there is a map delta from X sent to the product of X. Then the image of the map is directly closed in X times X, which the X is separated. So for the orbicons correspondence theorem, so we let the toric variety of fence X sigma, then the cons of the fence has a bijective correspondence theorem correspondent with Tn orbits in X sigma, which you can see the cons of the fence is have bijective correspondence. So here's the example. So we take back the previous diagram, and then the orbit so we choose sigma 0. The orbit of sigma 0 is the product of C star, is C star 2. And then for the orbit of the sigma 1, which is C star times the 0. And also for orbit of 2, which is 0 and C star. And lastly, for the orbits of the orbits of the cons 3, which is only the 0 point. So you can see that the orbits and also the cons have a bijective correspondence here. And there is a TF-AE statement from here, which is the X sigma is equivalently isomorphic to the product of non-trivial torus and toric variety of smaller dimensions. There exists a non-constant morphism, which is X sigma sent to a morphism to C star. And also for const in fence in one dimension, which sigma 1 is denoted as a one dimension of fence. And for every const in one dimension of fence, we can say that the const is a ray, or you can see only a text axis, which means like something like this const1 or even const2 is in one dimension. Then the U sigma, which denoted as the minimal generator of sigma, intersection of sigma 1 and n, that each do not span in the vector space NR. So lastly, about the toric morphism. So the definition of toric morphism will let two torus Tn1 and Tn2, such as the affine toric variety V1 and V2, that there is a morphism from V1 to V2 is toric morphism if and only if the map from Tn1 is subset of Tn2, which there are restrictions such as the phi of Tn1 which sends Tn1 to Tn2 is group homomorphism. So here's the remark. Let fence 1 and fence 2 for fence in the subset of N1. Then this compatible map, which phi of N1 to N2 if and only if the cons sigma in the fence I that E is the subset of the cons 2. So the form of mapping shows above can apply in any toric morphism of the X sigma 1 and X sigma 2. So that's all from me. Thank you. And now I would like to pass the mic to Jack. Okay. Numeric. If X is serious, so that's numeric. Because I'm not quite very sure about the number because I just get the number from these definitions. So if what is numbering, I think if only if the ring is irreducible. And what do you Alden? Can you Alden? Mm-hmm. Mm-hmm. I'm not so sure. Mm-hmm. Integrally close. Is fields of X is integrally close with respect to field of fractions. Okay. Not so sure. Yeah. Mm-hmm. 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 Yeah.
Basically, this particular we can any molecule and it is in the fluid fraction, but it is also in the ring more active. You are implying field fraction is splitting. It's splitting. You're talking about splitting. Field fraction. I mean, like, whatever the monic polynomial write down in this ring here, the root of this polynomial should already lie inside this.
Mm.
This is what it means by integral.
Mm. Okay. Thank you. Okay. Thank you.
Yeah, click it. It's good. Wait,
Oh, no.
delete this video.
Delete lah.
Yeah, got it. Yeah.
Thank you. Okay. Hi. Good morning, everyone. My name is Li Chan Jack, and student ID is MNT2302056. Today I will present a topic that is a divisor in a toric variety. Okay. I will separate the three part into the two main part, which is a well and a Cartier divisor on the normal variety and toric variety. And the second part is I will talk about the relation between the line bundle, base point free, and the numerically effective NEF and the intersection product. Okay, just have a recall. We start with the concept of the discrete variation, which is the function defined via function nu defined from the k star to z, and then specify the following properties here. Okay, then we have the discrete variation ring dvr that is a correction of all x in k star such that the variation of x is greater than or equal to 0 and union of the set of 0. Okay, let's see the important definition here is a prime divisor. A prime divisor is on a irreducible variety X is an irreducible closed subset of core dimension 1, meaning that the dimension D is equal to dimension S minus 1. Then let we see the definition 3, let the D be a prime divisor, and then we have a subring OXD of the CX defined by the correction of function in CX, which is defined on the open U with the condition U intersect the prime is not empty. Okay, next we define the well divisor here. A well divisor is a finite formal sum of prime divisor with the integral coefficient AI. Then a well divisor is an element of the diff x. So the mean diff x is a correction all the well divisor. And we call a well divisor is effective if the coefficient AI is greater than or equal to 0. And then we have the support here is a union of all the prime divisor with the non-zero coefficient. Okay, sorry. Okay, now here have the lemma. The lemma say
if the f is in the Cx prime, then the variation of f is equal to 0 for all but finitely many prime divisor D. Here, why the f is live in the Cx star, because if the function f is a zero function, then the variation of 0 have the infinite prime divisor, right? Then so the f cannot be the zero function, so we live in the Cx prime. Okay, next we recall the thing lecture we learn already. So we define the divisor of the function, which is the summation of the prime divisor with the coefficient, that is the variation of f. Then we say the div f is called the principal divisor, and we denote this new notation div 0 is a set collect all the principal divisor. Okay. Then we say a two divisor are linearly equivalent if their difference is a principal divisor. Okay. Then we define the Cartier divisor. The Cartier divisor is a well divisor that is a locally principal. Then that is X has an open cover UI such that the D restricted UI is principal in the UI for every I in I. If the D restricted UI is equal to the div Fi restricted UI for some I in I, then we call the UI Fi is the local data for D. So we have the Cartier divisor, we have formed a group called CDiv X. Then we have the below inclusion here. Then this obviously the CDiv X is live inside the div X because the Cartier divisor is an element of a well divisor. Then the div 0x is contained in CDiv X is because the principal ideas is obviously local principal, so live inside the contained in the CDiv X. Okay, next we define the two group, which is a divisor class group equal to the div x quotient out the div 0x. And the pk group is the c div x quotient out the div 0x. Then the difference is the div x and the c div x. If there is equal, then this two group is equal. Okay. Later we will talk it. The div x equal to the CDF. C div x. Okay. You just mean the well divisor is Cartier divisor. Okay, later we'll talk. Okay, next the theorem is here. A very important theorem. If the local ring OXP is a UFD for every P in X, or we can see the second one, if the X is smooth, then the well divisor is Cartier. Okay. Okay. Okay, next we have the ray rho in sigma 1. Okay, give the codimension 1 orbit in of the row whose closure is defined by we define the D row. It's the closure of the orbit row. And then we have the variation V nu row equal to the nu D row. I just change a little bit. This is for the toric variety. Just now we talk about the normal variety. Okay. Then we have the two things just now Eugene have mentioned. There is a minimal generator U row and the character x to the power n. Then these two we can do something. We can do the variation of the x to the power m is the inner product of the m and the u row. Because if we have the variation, then we can define the diff of the x m. Then which is the summation of the prime divisor with the coefficient, which is the variation, we just substitute the inner product into the summation. Okay. Okay. Okay, then we if we take the integral linear combination of this B row, then we get what is called a torus invariance well divisor here. So this gives us a subgroup of the full well divisor group, which we denote as the diff Tn x sigma. And the definition 12 say on a toric variety, the Cartier divisor as are also the well divisor if in fact they can always be written as a sum over the ray of the fan. So this is especially convenient because it reduces the study of the divisor to understanding just a few combinatory and the coefficient of error. So in the toric case, the Cartier divisor are fully described by the integral data on the ray. Okay, this is an important proposition also. Let X sigma be the toric variety of the fan sigma, then the following are equivalent. So every well divisor on X sigma is a Cartier if and only if the Picard group is equal to the divisor class group, and equivalent to the X sigma is smooth. Okay, the A equivalent to B is obviously right. Just now we have talked, if the well divisor is Cartier, then the diff X is equal to C diff X, okay? Then the two group is equal. Then one thing is easy is C implies to A. If the variety is smooth, just now we say the theorem, the well divisor is a Cartier. Okay, and other we can, if you're interesting, you can see the proof. I don't prove here. Cartier implies well. Well, Cartier is the element of wow. Cartier come from wow. When Cartier, when the divisor is a locally prime visible, and then the well is a Cartier. Okay. Okay. Next we have definition. We have the function phi defined from f to g be a homomorphism of the shift. And then we say the function phi is to be injective if for any point p in X and any open subset U containing P, there exists an open set V containing P such that the function defined from Fv to Gv is also injective. Then we say the function phi is subjective if for any point P and any open set U containing P and any section G in GU, here there exists an open set V in U containing P and a section F in FV such that the function phi VF is equal to the restriction map from the GU to GV. And okay, now here have the definition of smooth. If the X is smooth or all occurring OX row are UFD, the definition of section, a section of F over an open set U, an element of FU that is defined on a U and satisfies certain properties, like this of the restriction properties. Okay. Okay, next we have the definition in a sequence. We send the I minus 1 to Fi with the function di minus 1 and send the Fi to Fi plus 1 with the function di. It's said to be the exact at the Fi if the kernel of di is equal to the image of the di minus 1. Okay, let's say a function. Introduction. Oh yeah, I saying that. Oh, I heard me say. Thank you. Okay. I is the index. Okay. Okay. A line bundle is a vector bundle of a rank one. So obviously it's one dimension. So why one dimension line? So why we call the line bundle? Okay. Okay. We have a theorem here. Okay. On a normal variety X, every Cartier divisor define a line bundle, which is the shift XD. Okay. Then, if the L is an immutable shift, then there exists a Cartier divisor D with the L isomorphic to the shift OXD. And there exists a line bundle whose shift to the section is isomorphic to L. Okay, let's see the definition. If L is the line bundle, then let the W is a subset of the tau XL. Then we say W is a base point free. It's very important. If for every point P, there exists a section S in the W such that the SP is not equal to 0. This is best point free. Okay. To define the numerical properties of a divisor, we introduce the intersection product. So we let D be the Cartier divisor and the C be the complete irreducible curve. Then we define the intersection product of D and C is equal to the degree of the function phi star of the shift OXD. And then the number, okay, then this degree is the number count the intersection of the D and C with the multiplicity. Okay. And next, Cartier divisor D is called a NEF, NEF, the numerically effective if the intersection product of D and C is greater than or equal to 0. And C is the irreducible complete curve. Okay, then the NEF divisor never intersect the curve negatively because from the definition, greater than or equal to 0. Okay. Okay. The last thing is a very important theorem. We connect all the base point free, connect the NEF and the intersection product together. Okay. Let the D be a Cartier divisor on the toric variety X sigma. Then the fan is a sigma has a converse support of full dimension. Then the following are equivalent. We say the Cartier divisor D is a base point free if and only if the D is a NEF and if and only if the intersection of D and C is greater than or equal to 0 for all torus invariants. Okay, I want to talk a thing is and this is the special for to the to the toric variety because in general the NEF and the base point free are not equivalent. Okay, on the toric varieties is equivalent. Okay. Then this is my part. Thank you.
What's the ego and ego?
Oh, zero is the okay. We have a ray is row right in the sigma one. A row is the ray. The ray in the sigma one. Yeah, which is the coordination one. Okay, and zero is a closer orbit of row.
Yeah.
This here.
But
Sorry. Let me see. Yeah. Yeah. This the zero I define here within not the closer of the
So gamma one, I mean sigma one is the of one dimension. What is the point? So it's like infinite range.
What dimension like?
Infinite range. Infinite range. Infinite range. Yeah. And then you pick a ray. And then give the four dimensions you want to support it. So rho is a ray.
Yeah.
What does it mean by give the four dimension one of it?
So
Somehow you give a four dimension.
sorry, how to give the four-dimension one orbit of the whole row.
Yeah.
See, like the cone is a line, right? Then the orbit is a correction of the cone,
Correction.
right?
What is that?
What is the sorry, let me think. Just now Eugene have given an example, right? The orbit orbit is sorry, sorry, don't remember the different definition. The orbit. Like I can write the whiteboard. Just now Eugene say like this, they have this E1, E2, and then the orbit. I'm not sure my notation is correct or not. It's a correction of the E1 and then X 0 for the X like this, and maybe like this, the orbit. Okay, the cone is like this, right? Okay, the cone is 2, cone and then 3, and the 4 is origin. The orbits are defined like this. So
Bit of the
I think like this. I think just now example. Or I wrong something.
what's the orbit? What's the group action? There's a group action. There's group action. Why is it called orbit?
Let's call orbit. And
Your E1 just now was just starting from 0, x and squared, but now you want to take
experience. Okay.
Yeah. Wait, that's 0.
This is sorry.
Okay.
Okay.
So this orbit has nothing to do with group action.
Yeah.
Your group say yes.
Yes. There's my wrong. I don't worry.
Which one? Yeah. I don't know. Why is the relation? What's the relation with orbit? What's the group action? And what's the action? How it depends. Yes. So multiply by scalar. But why after the orbit? So okay, so in the Newton case one, what's the scalar? Yeah, sure. This is the range. Okay. So what's the orbit of E1 now?
Yeah. How do you compute? All right.
Is the way it defined is that this is actually a map from like ah, then you actually apply um, map from C star to C star. And technically this map actually induce a multiplication, something like that. L. This L here is actually depending. That's how you define the inner product.
So this action will act on that.
So this is not the action. This is just the last is the action is also another thing. So the action depends something like, for example, V intersect V star. One, two. So this is our collection T1, T2, element of C star. And then this tip it acts on V equals to V, where it takes X, Y, Z multiply to dx, T1, T2, Y, then T3, T1, T2, Y. So it depends on the how you play around with the lattice and the action and so on. It's a lot of things in the background.
So that con is not right here.
No. This thing,
Just the thing that you find around.
yeah. So you have the theorem, as Eugene said, the orbit cone correspond. So every cone corresponds to an orbit. So and the orbit is based on this action of the torus. By some point, this point is very weirdly defined, right? But in essence, you could build up.
Oh, you mean okay? So where do you start the orbit? You just start from the original, like the
So yeah, so
the con that I mean
like for example,
so your basic toric varieties, right?
the basic Toric variety at X respect to some fan. It's really just a union of U sigma. Sigma. So this U sigma was defined by Eugene. The affine semi-group thing. Then you define it and you go through around the fan. Sigma.
So your T will add on this thing to the.
Yeah. So you could actually, I guess, add
So if you change any fan, then you will get
a different
a T. Huh? It's your part. Okay.
Also, we're explaining.
Okay.
Okay, but
So,
Thank you.
Hello everyone, my name is Tan Yi Heng, student ID MAT2309X20. Today I want to talk about Toric version of Nonce data and canonical devices. Our discussion will cover motion construction, Toric ideal variety corresponds, color differential, cotangent shift, and also keyform and canonical devices. First, we discuss about Nonce data. We need to recall that the Nonce data in the projective version, what we have done is use R5 version, but the idea need to satisfy some relations. Okay, it is similar to our Toric version, so I will construct the Toric variety as a quotient of R5 space. This will give an ideals. Then we can now non-cylinder in similar results. Main idea used here is the invariant property. Okay. Now, given a group actions, we have the following called the G orbits and the ring of invariance. If F is an element in these invariant rings Rg, and X is an affine variety of coordinate ring R, then we have a well-defined map. Just send all the G orbits, to its function values. Moreover, we have the G orbits is isomorphic to the affine variety of ring of invariance, but note that this process not always give a good things. It needs to satisfy some conditions, but I will skip it. It's some technical part. Now I turn to our Toric case. We first show this as a sequence here. We apply this mapping to the sequence, this home Z C. We get a new address sequence. This gives a natural way to think how we construct a quotient. We can choose G as a group here. That's but why we can do it? There's some technical part. I skipped it. But the idea is the prime divisor D row are torus invariant. That's why we choose such G. For G, how we define just now, we can calculate it using the primitive generator of rays here. You can see the for basis EI of M, we can generate the G as a distinct. Then okay, now later we will see how to compare. Now we already have a group and the affine space just a product of the complex number. The things we haven't find is the exceptional set. Why we don't just quotient out all affine spaces? The reason is there exists some bad points. Things like the projective space, we always take away the origin. But sometimes we need to take away more points. Later I will show it. And also important things are actually G and affine space only using the rays, but different fan can have some rays. So how we determine a unique Toric varieties? That's why we need to do the next things. So we first define a total coordinate ring. It's a C algebra where the generators are the variable assigned by the rays. Then we can have things called exceptional monomials. For any cone in the fence, we define the exceptional monomials as product of variables such that the corresponds ray not in that corner. The next thing is we can specify the uniqueness. The 11 ideal, we can specify the uniqueness. An ideal generated by those exceptional monomials, the exceptional set is the zero locus of the 11 ideals. Okay. For the 11 ideal, some nice property holds. For every face in a cone, exceptional monomial of that space divided exceptional monomials of the cones, so that we can use the maximal cone to generate it. Moreover, if we know what are the rays, then the irreverent ideal will uniquely determine a band, and a band uniquely determine a Toric variety. Now we can go on to the quotient construction. We define a Toric morphism pi from affine space, take away the exceptional set to Toric variety. How how we do this map, we send all the G orbits to an equivalence class. Then we take a function value on that equivalence class. Okay. This morphism has some nice property here. First, that this Zariski dense open subset of the varieties. The pre-image of this open set quotient out the G is isomorphic to U itself. Next, if the Toric variety is simply shown, the quotient things will isomorphic to the Toric variety, and also the all G orbits are closed. Also, we send some condition is that Toric variety is simply shown. Then, if W is subset of, then if W is subset is a closed and G is subset of C sigma and minus the Z sigma, then the pi W is closed in the Toric variety. Okay, now we give an example with the affine space. Trivial case. Consider ray generator 1, 0, and 0, 1. And the maximal cones also generated by these rays. Then we get that G is just 1, 1. So it's no relation here. Total coordinate ring is D, X, Y. And the inner ideal is 1. So the 0 set is empty. This Toric variety is just 2. Next example is the simplest non-trivial case. Consider a fan with rays generated by 1, 0, 0, 1, and negative 1, negative 1. And the maximum cone, just take all possible of 2 cones. We can calculate it. We can calculate that G is a set lambda 3 tuples, where the lambda is an element in C star, so that the equivalence relation is the line through the origin. Total coordinate ring here is C with 3 variables x, y, z. Irreal idea is generated by x, y, z, so that the 0 locus is 0, 0, 0 origin. So this variety is isomorphic to C3 take away origin, quotient out the line through the origin. So it's just a projective 2 space. Now we complete the next example. Let the pen with rays generated by 1, 0, 0, 1, and 1, 1. You may observe that this example is quite similar to the previous 2 examples. It shows some relation between them. Actually, this is the refinement of our first example. We add 1 ray, which is add those 2 rays and the maximum cones. Here we replace 1 variable to the new rays. Since they have 2 variables, so we have 2 cones here. We can calculate the group G is lambda 3 tuple, but the last coordinate need to take the inverse here. Then the lambda can be any non-zero complex number. So the equivalence class like this. Total coordinate ring is just C, X, Y, Z. Irreal ideal is generated by X and Y. So the exceptional set here is 0 locus of irreal ideal, which is X equal to Y equal to 0, which is 0, 0 cross complex number. So the Toric variety is isomorphic to this quotient. Then we can observe that for G not equal to 0, we can take that. We can take Z, we can apply Z. Then the point become ZX, ZY, and 1, which is isomorphic to C2 minus the take away the origin. And for Z equal to 0, because then XY cannot both 0. So this becomes lambda X, lambda Y 0, which is isomorphic to the projective 1 space. So you can see is actually for Z equal to 0 is actually the blowout of C2 at the origin. Blowout of C2 at the origin. The function value is equal to P1. Okay, so that's why we consider it. So that's why we consider this Toric variety isomorphic to the blowout as a C2. Now we have the quotient things, so we can go through the knot cylinder. Actually, this is very similar to our class study, but we have more conditions here. This is a general case to our study. The statement states that for a simplicial Toric variety with total coordinate ring S, if ideal is I is a homogeneous ideal subset of S, then the zero locus of I equal to pi x in the pi x in the Toric variety such that fx equal to 0 for all in the ideal is a cross variety in the Toric variety, and every cross subvariety of Toric variety arises this way. How about non-simplicial case there? We can just replace the pi x in the Toric variety by p some point p in the Toric variety such that there is a x such is equal to the pre-image of pi image of p. Okay. Oh, sorry. Here is the Toric knot cylinder here. For a simplicial Toric variety with total coordinate ring R, S, and an irrelevant ideal B sigma. If I is a homogeneous ideal, then the zero locus of I is empty in X sigma if and only if there exists a L greater than or greater or equal than 0, such that all possible product of L elements in irrelevant ideal is subset of ideal I. The proof is simple, just using the alpha case. Now, next we have a bijective corresponds for simplicial X sigma. Every cross subvariety in X sigma corresponds to a radical homogeneous ideal subset of irrelevant ideals. Okay, we finish our first goal now. We go through next things, a totally different story. First, I introduce what is the color differential. Let R be an C algebra. The modulus of color differential of R over C, simply call omega R over C, is R modulus generated by dF or OF in the R and satisfy the linear and product rules. You can think like taking differential you have learned in the calculus. For example, if R is C algebra generated by n variables, then omega R over C is isomorphic to direct sum of R times dxi. Next, we introduce an exact sequence here. For psi from R to S surjective kernel I, we have a sequence of S modules. From I quotient I square to S tensor omega R over C to omega S over C to 0. For F is in the I quotient I square map to 1 tensor df. To know why this sequence exact, we can define a mapping phi for R. For R in omega R over C, the mapping send S tensor R to the sum of S times psi G I times df d psi fi. Give example. For R in CXY, S equal to CY, then the sign have kernel X. For R equal to GXY dx plus DHY dy, psi S tensor R equal to S times G0Y times D0 at plus S times H0Y times dy equal to second part because the first part is in the kernel. Next, we let for Rf be a localization of R at the non-important F in R, then the omega Rf over C isomorphic to omega R over C tensor Rf. Then the cotangent shift omega Fu is a structural shift modulus defined by taking the section of shift on the open set U. This is called a one form. Now we consider a P form. E form is just the wedges product of one form. We define the canonical divisor by taking double dou of the M form. M is the dimension of variety. For the toric case, we have a nice thing here. The canonical shift of a toric variety is isomorphic to the structure shift on negative sum of torus invariant prime divisor of ray rho in sigma 1. This is useful for our next session. Recall why we had talked there. We construct a toric variety as a quotient. Toric ideal variety corresponds, say that each closed subvariety is correspond to a radical homogeneous ideal subset of irrelevant ideal. The toric need to be simple. And we also introduce differential using color differential and talk about potential shift, E form, and canonical divisor. That's all. Thank you. Here is my reference. Okay. Right. Okay.
How do you get the capital G from?
Oh, you can calculate here. Actually, it's just taking we just taking this this thing. So rho 1 equal to 1, 0, rho 2 equal to 0, 1, and rho 3 equal to -1, -1. And we take a standard basis of x2 1, 0, and 0, 1. So that first G satisfy two equations here. First is T1 1, 0, 0, 1. That's 3, 1. T2 is 0. T3 is -1, -1, and taking 1, 0. Then it put 1, and T2 I simply 1 equal to 1. So we have two equations here. T1, T3 inverse equal to 1, and T2, T3 inverse equal to 1. So that is T1 equal to T2 equal to T3. So it's just lambda, lambda, lambda. This one?
Yeah. With the relation, so you have
Just relation, just taking all the G orbits. G is the lambda, 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 and x, y, 0 equal to lambda x, lambda y, lambda z.
having what's your inner product?
Or inner product. Inner product is just z2. Inner product in z2.
What's the scalar?
How to say? Just component wise, dot product, yeah. Okay. It's good. Yeah, any question here? Question.
So the claim is the G.
Yeah.
So how to view this G as a homomorphism from vector?
There's some technical part I missed. I skipped it. Yeah, actually it's from here. It's from here. Actually, it's from here. We use the torus invariant here.
The first exact.
The first exact sequence. Let me find the picture I already give. The first. Oh, the map. Okay. Yeah. The first map is just map M, the element in the lattice. We map to the divisor of the chi M. Divisor of chi M. just let M divisor of and this divisor of chi M just sum of row input what 0. And the second one, the second man send that second man send a TN variant divisor to the divisor cluster. So actually just send 0 to divisor cluster. This 0 is a Toric similarity.
CL.
Hmm?
Character.
Character
Oh,
group.
what's that?
Character group.
What device?
Class group. Class group.
Also, there's another name. Because I saw his slide, call it
Character group is
same thing.
I think the character group is just we taking the home list become a group like maybe M or character group is this one. Not sure. I'm not sure.
I mean, like this CL is character group or device group?
It's the class group. No.
Class group?
Class group.
I thought you labeled.
No, it's because we imply this generator this thing. Yeah. It become a totally different thing. Not class group now. We invite the home jack to the class group. It become different things. Not same things now.
Wait, so CL is a device group?
Yeah, divisor group.
Somewhere.
Where?
Can you go through your screen? Yeah, first one. CL of that X is a character.
I think it's just
Character group or particular device group?
maybe I'm not sure. I'm not sure here. I'm not sure. Because the maybe the class group has some nice thing in the group G but in the Taurus is the divisor group. The other class group.
I mean, in this special case,
Yeah.
device group become.
I think so. I'm not sure. Maybe is this come from the apply the home tag. I'm not sure.
You're not sure?
Yeah,
You
because
writing it?
I'm not sure because this is like a dual things and
Why are you writing?
I writing in the report. I add some explanation to the appendix there. Yeah, appendix.
No,
Because
mean
I think
like. Okay, wait. So do you understand it? Why is it true or you don't understand?
I'm if the I cannot understand why apply this can get a class group. Yeah, can get a character group here, but
What's the definition?
oh
If you don't know the definition, then how you gonna prove? Maybe then cannot prove. Right?
he used a lot of things in the previous chapter.
But are you gonna like explain it in your report?
Yeah, I know.
Huh?
Yeah, I will explain it.
Yeah.
Yeah, it's a big question here.
I think you predict the
Mm,
report.
Yeah.
Do you do exercise like
I have to do exercise.
do exercise?
I have to do exercise.
But I see you for keep all your prep. But
Not sure.
I'm not sure. You did do exercise.
I have to exercise, but
What kind of exercise?
walking.
Walking. That one exercise we also do. When you talk, you I think it's important to keep your physical well.
Okay.
Yeah, otherwise you cannot. Can't even talk at you. Okay. Next one, thank you.
Um, Good morning to all of my classmates and Dr. Nghi. So today I'm going to talk about shift cohomology on Toric varieties. So before we get into our content, so I will outline what I'm going to talk in the lecture session. So first, I'm going to talk about some background on shift cohomology, and next I'm going to talk about a little bit on check cohomology, and thirdly, I'm going to talk about shifts on devices and some cohomology of Toric devices. Next, I'm going to talk about some vanishing theorems, such as the demerger theorem, which is a good vanishing theorem for Toric variety, I mean the cohomology of Toric variety. And next, which is our main character here, which is a shear duality. I'm not going to show the proof here because the proof is quite technical. I think it's like 3 pages here. But it's the shear duality for the Toric case and some examples. And let's begin. So what is a shift? So recall that if we let X to be a topological space, a shift f of X assigns to each open set U, which is a subset of X, a set FU, meaning if you give me a space X and for any open subset of X, say U, you can assign it a set FU, meaning FU is a set, and we can do morphism between these FU. Suppose there's another subset V, and which is a subset of U, and there's a for shift to the shift must have a recession map with say rho, and this rho is actually a morphism between those sets that I defined just now. There's a morphism between FU and FV in this case. And for it to be a shift, we need that restriction map to satisfy the following, which is if we take the rho UU must equal to the identity, and if there is a third open set, which we set W, which is a subset of V as well as subset of U, then it must satisfy the composition of maps. Next, in order to let it to be a shift, it must first satisfy the glowing property. Glowing property, I mean, if there is an open cover UI covers U, and we denote the element of FUI as sections, which is SI in this case. If they agree on the intersection, then they must glue linearly to a section X in the FU. So this is what basically a definition of shift. So like what I think is mentioned in that presentation. For shift, there's a homomorphism between shifts. So if we have suppose we have a source as a sequence of shifts on X, and there's a homomorphism between the shifts. And actually by some proposition in chapter 6, which is in that part, but I didn't show it here. They say that they could give rise to an exact sequence of global sections as follows. And the global section basically means here, instead of taking the subset U, we take the whole space X. That's why they call the global. And basically the shift cohomology is capture the failure of the last
last map between the gamma x g to gamma x h to be sedative. It captures the value of the. And next, so what is a shift homology? So a shift, suppose there's a shift f on a variety x, and it has a shift homology group HP, and we will define it later. So first, we begin with an exact sequence of shifts, 0 to f goes to I0, I1, and so on. And we said this I is injective if given a shift homomorphism between alpha between H and I, and then if there is an injection between H and G beta, then there exists a shift homomorphism theta, making the following diagram commute. If the diagram commute, I mean if there exists such diagram and if the diagram commute, then we say the shift I is injective. From the first exact sequence, we can further get the complex of global sections from that resolution, and we will get the following long exact sequence. And the complex, what do we mean by the complex here? It actually means the map between the shift, particularly, I mean, they need to satisfy the composition to be equal to 0. I mean, the TP plus 1 when composed with DP is equal to 0 for all P greater or equal to 0. So the P shift homology group of F is defined as follows. It's basically look at the kernel of DP and quotient out by the image of DP minus 1. And for the group, for P equal to 0, we will let D minus 1 to be the 0 map 0 to gamma X I0. So that's the construction for shift homology. So now we get into our check homology. So basically, why they introduce check homology is because check homology allow us to compute by hand instead of looking at this abstract definition. So what check homology does is actually they look at the open cover of the variety, and suppose there's an open cover U of X, and we let the I to be the index set for that cover. And with that all that assumption, then we can view this shift homology in terms of check complex. And we define the group of P check quotient to be the direct sum of the shift and carries over the intersections of those open covers. So now we can build our check complex, which is similar to the shift homology case. And similarly, the P check homology group can be computed by looking at the kernel of DP quotient out by the image of DP minus 1. So how does a shift associated to a divisor, or I mean how a divisor associated to a shift? Suppose S is a normal variety, and D is a formal sum of D0, which is a prime divisor. I think this is introduced in EHEM part. So the shift OX DU, meaning if you send a send a open set U to this, let this OD carry over the U, then ODU is defined to be the set of function from CX star, and it must satisfy the following, meaning the diff F plus the divisor, which is stated to the domain U, must greater or equal to 0. And I think in this case, for Cartier divisor D, this is called the line bounded, which is mentioned in jet presentation. And so what is a check homology of Toric divisor? So basically for Toric divisor, we choose the open cover to be the set of maximal cones in the fan. And in this case, we can define our check complex in terms of Toric divisor. I mean Toric variety. So basically, it's defined similarly as this. As that now we can associate it with a shift on the divisor, with a divisor in the Toric variety. Actually, for computation purpose, actually one can look at the gradient of on cohomology. Actually, this is defined as follows: the 0-degree cohomology group of this for this case will be computed as for some complex number times the character map in Toric variety, and if the condition satisfied. But I won't show it here, but this is some remark. So in the case of P2, we let UI to be the fine upon cover correspond to sigma I, which is the cone correspond to for example, in P2 we have U0, U1, U2, and for each of U1, for each of UI we define it to be Si not equal to 0. So we do not, in this case, we did not our Uij to be the intersection of Ui and Uj, as well as the triple intersection U0, 1, 2. Then we have the following check complex. By the previous definition, one may proceed with compute those direction, and actually this computation they somehow use some decomposition or chambers, but I didn't show it here because I think it's very invest kind of waste of very lot of time. Next, if we look at P1 is similar, we can use U0 and U1 to cover it, so we can take it as open cover correspond to our cone. And from Harshon, I think section 5, there's a famous remark. It gives us the following result: the 0 cohomology group of P1 associated to achieve OD is equal to KD plus 1 when PD greater or equal to 0. The D here is the divisor, and K is the field the P1 carries. For example, our case about P1 looked at particularly on C. C. And the first degree of cohomology group is equal as follows. So I will introduce this definition because in the demerger theorem, it's defined, is tested by this under this condition. So a well-divisor D on a normal variety X is called Q Cartier. Is for some positive integer multiple is Cartier, meaning for suppose D initially is not Cartier. For example, if multiplied by 3 and 3D, and we check that is a Cartier, then we say it's a Q Cartier. And next, we define the divisor D to be enough if the intersection product is greater or equal to 0 for all complete irreducible curves C subset, which is a subset of X. I think it's defined in the jet presentation. So in the case of Toric variety, we actually could characterize those Q Cartier nerve divisor as the following. And suppose D is equal to the former sum and take it to be a Q Cartier divisor on this Toric variety. If sigma has convex support, then the following are equivalent, meaning if you give me a nerve divisor D, then it is associated to a support function, which is convex. The absolute value of sigma means here the support of the fan. Support basically means the union of all the cones in the fan. As well as the second statement, for example, for some integer L greater than 0, the LD is Cartier and best prime free. And this is a demerger theorem, which is one of the vanishing theorem. Why is it called vanishing? Because basically it means for some degree P is equal to 0, and it has to satisfy some condition. For Toric case, if our D is a Q Cartier divisor and the support is convex and D is nerve, then we have the following result. And for the sketch of the proof, we use the previous lemma, which I mean this lemma. So if D is Q Cartier and D is nerve, then it implies its support function 3D is convex on the support of the fan sigma, and we assume D to be Cartier with convex VD, and we define the following set, and we let UV from this set such that it satisfies the defining set properties. And we can play around with the convexity of the V, and we can find that actually VD sub this V to the power sub this set particularly is convex and then contractible. And sorry, I think the notation I did. You change. I think I sent you the letters for here. Never. So I think the sigma here is the VD, and the the sigma M and sigma N is replaced by the VD, V1. And so V is contractible and its radial cohomology is equal to 0. And actually, I hide one theorem behind this, meaning the theorem states that there's a natural isomorphism between the reduced cohomology and our usual homology. Basically, the reduced cohomology means it takes care of the case that the single point need not to be single point need to be 0. It must vanish in our cohomology theory. I mean, because in our usual cohomology theory, the cohomology of a single point is not necessarily equal to 0, and in reduced cohomology, that let it to be 0 to avoid not those trivial cases. And by this contractibility, we have this reduced homology to be equal to 0, and therefore HP is equal to 0. We prove our demonstration. Next, let's look at some examples on PN particularly. So we let D not to be the torus invariant divisor corresponding to the ray row 0. And if we consider the Toric divisor A times D naught for some A equal to 0, and if since A D 0 is best point free, and by demerger theorem we have the following, and actually we can prove that actually A is linearly equivalent to D0, linearly equivalent to D1 as well to Dn. So A OA D0 is equal to OA by linear equivalence. So by demerger theorem, we get that the cohomology of Pn associated to OA is equal to 0. This is our shear duality for Toric varieties. Assume that our Toric variety is a complete Toric variety of dimension n. Then we have the following. Particularly, we'll look at the first case. If this is a q-partial divisor and case k associated to this Toric variety is the canonical divisor, I think it's defined in the Ehem presentation. Then we have the natural isomorphism between the dual of the cohomology and the n minus p degree cohomology group of the Toric variety. The dual here, I mean, is basically the home space between the usual cohomology HP to the field it carries. I mean, the field of the Toric variety lifting. Sorry. Yeah, let's look at this example. Suppose our canonical divisor to be O minus 2, then by shear duality, we can compute our dual cohomology of 0 degree. And by the previous this result, we actually can sub in our D equal to -3 into this, and we will get that actually is equal to K2 by this result. I mean, by this, the right hand side, if we sub D equal to -3, we get K equal to K to the power 2, which means H1 is equal to K2. The field, for example, if you think it, you can take K equal to C, the complex number space. So we can get our H0 is equal to K2. I think you tackle here. I think the H0 should be to the power of the dual space. Yeah. So basically, shear cohomology capture the global structure of local data, and Toric variety allow us to see some complementary methods, and divisor shift and check cohomology make the computation explicit, and the measures and shear duality allow us to compute the complicated cohomology group in a more convenient way. So that's the aim of my presentation.
Before you do the check homology, right? So what's the differential input on your shapes?
Shift homomorphism. Shift homomorphism. Kind of shift homomorphism. What kind of shift? I think it's just basically yeah. You mean the map between the shift, right? I think for me, I think for me, I think it as a shift homomorphism, but you mean if satisfies some, yeah, yeah. In this case, if it need to be a complex, then yes, yeah. So you satisfy what property? What property? Okay. In my opinion, because in my opinion, because this FU, if we take it is a homomorphism in the group sense, I guess. In this case, in the user group multiplication. Yeah. Okay, wait. I think it's module. It's basically need to certify the module homomorphism. Yeah. Or what are they? Oh, okay. Yes. Okay. For one, I remember for one is if we times the scalar, then we can pull out from the if we input for example, phi is a homomorphism, then if we input it Rx, and we can pull out the R. That's one of the property of module homomorphism. I mean, yeah. I think I don't understand your question. Maybe you can. Yeah.
You haven't really tell the I think this D is a specific D, right?
Specificity.
Fixed D.
Fixed D. Okay. For now, I could not figure it out.
Because otherwise I couldn't.
Oh, I see.
Like I don't know what's the partner and the image of the map.
Oh, okay. I know your question now.
Like for example, the second last line there, what's the D? You tell us D plus D minus one. The 0 point. How about D0 is D1?
Yeah. For now, I couldn't figure it out. Yeah. Okay.
So the last one.
What?
Good morning, everyone. I'm Muhammad Faiz, and I'll be the last speaker from our group to discuss about the resolution of singularities of toric varieties. Okay, so let us start. So we're going to discuss like three things actually: the smooth and singular points of toric varieties, the star subdivision of a fan, and then the toric resolution of resolution of singularities. The toric here meaning the toric morphism as discussed from Eugene in the first part. It's a bit a while now, but it's fine. We go through it. So before we move on, we need to discuss about the smooth points of a toric variety and how do we define it. So one way, I guess, is you determine all of the points of an affine variety is smooth. There is the dimension, we calculate the dimension of the Zariski tangent space. But here we are considering toric varieties. And with toric varieties, it comes with respect to a fan and especially with a cone. So here we are going to discuss something about an affine toric variety, the U sigma we keep on seeing here. So before this, we're going to define what is a smooth cone, and also there has been a mention of the simplicial cone. Okay, so sigma is a strongly convex rational polyhedral cone. Then it is smooth if its generators form a part of a z basis of the lattice. If this is in the lattice, not in the vector space. Then sigma is simplicial if its minimal generators are linearly independent over R or the vector space NR. So this vector space is not the lattice NR, but it contains the lattice. Okay, so why do we consider this cone? Well, in the affine toric case, they are equivalent. So given a strongly convex rational polyhedral cone, a affine toric variety is smooth if and only if sigma, the cone itself, is smooth. So now we have a description on how to determine when an affine toric variety is smooth. Okay. Sorry. So here it defines that in the first bullet point, if its generator form a part of a z basis of n. Okay, here is an example of a cone that is not smooth and it is not even simplicial. So it's generated by the basis vector u1 and u2, and also u1 plus u3, u2 plus u3 in the three-dimensional space. So it looks a bit weird here. The cone itself is the green part. The red part is actually an unbounded part. So it actually continues further. And this is not simplicial. As you can see, the generators are those arrays, or essentially E1, E2, E1 plus E3, and E1 plus E3. They are not linearly independent. Okay? So yeah. So now we have a way to determine an affine toric variety being smooth. But what about a general toric variety? And the general one is really come equipped with a fan. So here we're going to define a similar thing about a fan. So a fan is smooth if every cone in the fan is smooth, and the fan is simplicial if every cone in the fan is simplicial. Okay, similar to the previous case, but now in the context of a fan, and now the toric general toric variety. So here is going to talk about when is a toric variety. So the toric variety is with a fan sigma is smooth if and only if again the combinatorial data sigma here is smooth. And how do we show this? Well, just go through the to the affine case point by point. So when, for example, so it amounts to showing each of those affine parts U sigma is smooth, and each as if all of those affine parts are smooth, sigma is smooth. And when all of the cone sigma is smooth, then it forms a smooth fan. Okay. Okay. So now we have a description on when our toric variety is smooth. Here we wish to resolute the singularities of the projective variety. Sorry, the toric variety. So what is it? How do we do it? So given an irreducible variety X, the resolution of singularities of X is just a morphism from X prime to X such that X prime is smooth and irreducible, F is proper, that is to say, the pre-image of compact set is compact, and F induce an isomorphism of variety between the smooth points, the pre-image of the smooth point, and the original smooth points. And we further say that it is a projective resolution if F is a projective morphism. This comes to play an important role because what we show it is a projective toric morphism. And also a remark here, the subvariety Xing is a singular locus. So all of those non-smooth points. But how do we determine those points? Well, let's recall from Eugene, the orbit-cone correspondence. The orbit-cone correspondence gives us a description on how to determine the point of the points of the toric variety. And here it allows us to determine the singular locus and the smooth points of the toric variety. So the singular locus is really just the union of V sigma, where the sigma ranges over all non-smooth cones. And then the smooth part of the toric variety is really just the union of U sigma ranges from smooth cone sigma. And recall that V sigma is the closure of the torus orbit corresponding to sigma. Okay. 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 Before we move on, recall that from Eugene's part, there's a way for a we had to determine a morphism between toric varieties, which is to consider compatible maps between the vector spaces, compatible maps. And one way of doing that is, so one way of to construct a toric morphism is to construct a refinement. Soon we will see what exactly is a refinement, but what does it mean for it to be a refinement of a fan? But yeah, so that's our goal. We're going to keep refining our fan to form toric morphisms and soon create a smooth variety. Okay, so let us first start with this following definition called the star subdivision of sigma, of a fan sigma. So given a fan sigma in the vector space NR and the primitive element V in the support sigma intersect with the lattice points N, then the star subdivision comprise of these following cones, where it is just the original cone if V is not in sigma, or we consider the cone tau V, or in another way of saying it, the positive hull or positive linear combination of these two elements. But the cone tau V is going to be defined to satisfy some certain condition, where V is not in tau, then tau is in the fan, but V and tau must be contained in some other cone in sigma. Maybe let's look how we might look here. So this is one. This is a cone, and it also forms a fan with respect to its faces. Here is one primitive vector. Let's say V. It will form this following. It will form this following ray actually in this new in this new fan. This ray is constructed with respect to actually it will construct this new cone where this is V and with respect to the tau here, but it is contained in this big cone actually. So here I said V is contained in this big cone, tau is also contained in this big cone, but V is not contained in tau. So it will form the cone. Similarly, it also formed this other cone. And now we have created a new fan with two maximum other cones. Okay. So this is one construction. Here is also another. So then what is important here is that this star subdivision is a refinement of sigma. What does it mean for it to be a refinement? Well, let's draw something we are all familiar with, pizza. So a pizza comes with slices. So essentially, this is a fan. So it's fan the generator here. I won't shade all the regions there. But what it means to be a refinement is that it subdivides each of the original code. Subdivides here, then technically also subdivides here if I fill it up. But it implies that these new cones in this refinement actually belongs in the old cone from the previous one. So sigma prime is here. They exist. Sigma is sigma such that sigma prime is a subset of sigma. I hope people could see this. Could you guys see? Okay, good. So yeah, it contains in the previous one. So you make up final pieces of the old fan. And so here is actually an example from the previous case, also from the cone that we constructed. So consider the fan sigma with cone and its faces from example 1. Then sigma, the star subdivision with respect to E1 plus E3 is defined as follows. It's actually you see, it's actually down here is the vector. I think it's over here. So it forms this new fan. It's subdivided. But previously, we recall that was not simplicial. But here it is now each of those maximal cones are simplicial. It becomes a simplicial fan. So our star subdivision have gone through to construct a simplicial fan. Okay, why is this important? Before that, let's talk some properties with respect to the star subdivision. So the first property being that the rays of the star subdivision only include at most one other ray. Okay. And then the torus invariant prime divisor with respect to the ray mentioned in part 1 there is Q Cartier in this new toric variety. And also, as I mentioned before about compatible map, it induces a toric morphism. And this toric morphism is projective. This becomes an important rule when we want to show the resolution, because successive composition of projective morphism is projective, and we'll soon construct our resolution of singularities. Okay. Now, we have just constructed one stage of a subdivision. Here we'll actually able to construct a better refinement. Every fan sigma has a refinement sigma prime such that sigma prime is simplicial, not yet smooth, but it's good enough. The rays of this fan, this refinement is equal to the previous rays. Sigma prime contains every simplicial cone of sigma, in particular those smooth cones. Again, those smooth cones are actually simplicial also. And the important part here, sigma prime is obtained from successive sequence of star subdivisions. So this last part is actually just follows from number 4. So the induced automorphism is projected, but still not yet a resolution of singularities. So it's fine. The way we prove this, we apply induction, and induction on this in this manner, because we reduce how many torus invariant prime divisor that is not Q-Cartier. Because when we apply star subdivision, it becomes Q-Cartier. But here we only consider the rays from the original fan. And as recall, excuse me. Oh yeah. It at most includes number 1. The rays at most include one other ray. But if we are only consider the ray from the original fan, it does not include anymore. So here it will reduce and then reduce successively until we reach 0. And what happens when there are no Q-Cartier devices? This is actually from Jack's part, it becomes simplicial. Okay. So before we move on to the smooth part, let us give a good method to calculate, to determine when it is smooth, when is the cone is smooth itself, because that's all we need. So we calculate the multiplicity of a cone to be the index of this following group. Okay, and sigma with respect to, yeah. And how do we calculate it? Well, also I forgot to mention, this cone needs to be simplicial to make things work nicely. Okay, so the properties that we have with multiplicity of a cone is that when it is smooth whenever the multiplicity is 1. The way to determine the multiplicity, you only need to calculate the number of points the number of lattice points inside this boundary. It stops. Okay, it stops there. So you just need to calculate the number of lattice points inside that, polygon there. And also, I made a typo that it should be less than 1. And also another way of calculating it is using the determinant. And lastly, the phases preserve multiplicity relation. So if tau is the phase of sigma, the multiplicity is less than or equal to sigma. Okay. So now we are ready to find our projective resolution. We just need to find a refinement sigma prime such that it is smooth, so that it gives us a smooth toric variety. So, and this theorem says that we can do that, such that sigma prime is smooth. Sigma prime contains every smooth cone of sigma, and sigma prime is obtained from sigma by a sequence of star subdivisions. And again, by 4 follows from 3 to get a toric morphism. And then also the resolution follows from part 1 and 2 to get the projective resolutions. And how do we show that? We define something called the multiplicity of the fan to be the maximum of all the multiplicity of the cones. And when do we achieve smoothness of the fan? Is then when it is equal to 1. But star subdivision allow us to reach 2 conclusions. It reduces or it stays the same, but the amount of cones of this multiplicity becomes fewer. So if we keep repeating, it will reduce up to become 1. And that's where we achieve the smooth refinement or the projective resolution of singularities. Okay, that's for me. Thank you very much.
To give the tip.
Before asking Price question, maybe all the group member can come up, and then we can ask question to them. I think in my presentation tradition, student get to get bonus mark if you ask question. Yeah, so you could ask question to them to earn your bonus mark. So maybe you can send out the side instead of timing. Then I will start first. Picture later.
Okay.
I will start first. So Phies, so it's all the projective space toric variety.
Yes.
Yes.
The project is a Toric.
Okay.
So because it's a Toric variety, it must come with a fan.
Mhm.
Yeah. So the way.
So what's the fan for PN then?
So it's going to be. Yeah. So it's going to be generated. I use the word generated. Generated. E1, E2, E3 until the end. But there's also one there. Negative E1, negative E2, negative. Yeah. So it looks something like this. Blue color.
already showing.
Yeah. So you see the part from hang, but it's only
So P1, P2, yeah.
So it looks something like this. This is the fan in 2 dimensions. So this is P square. So there's going to be three dimensions, 3 1 dimension, and then 1 0 dimension.
So, and I think just now I saw the cone, right? Is this the cone?
No.
No?
No, actually, it's meant to extend. This is technically the convex.
Ah, right.
So, but yeah, it extends internally. And in
Okay.
fact, this is compact actually, right? P square is compact.
So like from this construction, how you build this? Long, is it long?
So again, it's sigma 1 equals to 1 P1, right? Need to find the dual, actually. The dual first, how does it look?
I mean, okay, I think a basic question is, so this is P2 is there. So basic question is like how you take this picture to that picture. This is P2, right?
Okay, P2.
Right.
So
basically this is A3 away. I mean like visually how you like.
or visually, like from the code itself.
Sure. I mean like what's this line correspond to those things?
Those like, don't think there's like a nice way of. Because it become the project in here is actually an open cover of UC.
So this UCMI is the one that we know, the standard R5.
Yeah, so U sigma was the spectrum technically. But the spectrum is actually the same idea of it required the F1 variety corresponding to
The two.
this essentially this.
So is this the standard R5 covering that we see?
Yeah.
Yes.
So let me try. So this one is, let's say, x0 equal to 0, and then this one equal to 0. And wait,
So
is it non-zero?
So this actually corresponds to the maximum time. So this part, like this big.
But these are open, right? I thought this is this closed?
Open.
This is open as well.
Open, yeah.
But this is a spectrum.
Yeah.
So it's a prime ideal inside here.
So this is going to be
So spec define an open set.
yeah, essentially the way the book describes spectrum is the idea of like for every F1 variety is the corresponding
to the
yeah. finally generated and also reduced. Same as the one you like the K algebra. So this is what it's trying to show.
Yeah, that one okay. That one I'm fine with that. Just that
it's a stack open the
Yeah, technically, actually more appropriately consider the spectrum of n.
maximum ideal. Oh, okay. Okay.
So in the book, it just says spectrum.
Okay. Okay. Yeah.
I think that a lot of the main machinery, it goes through the orbit corresponding. But the orbit corresponding, they're a bit hard if you don't introduce the something called the distinguish point.
Okay.
Yeah.
So this construction here is with Eugene, is it? Are you writing it down in your contract? The whole part here.
How to construct the projective, at least the projective here. And the projective here. Yeah. Yeah.
Okay.
okay. Any other question before we take a break?
No.
No. Let's take a break. So you guys can stay for photo first. So what time is it? Because just now we start late, so everything is delayed. So let's start again at 10:30. Okay, let's resume at 10:30. Yeah. Yeah. 什么东西？
他们10结束了。
应该反正我们的 our lunch time is quite long, so that's fine. Sure, okay. Well, you want to eat 2 hours? Yeah. Because people start late, man. So yeah. Okay. Yeah. So maybe 我们可以拍个照，做个记录。Which slide you guys want to use? This one. Toric variety. You can take with your slide. Yeah, this one. Okay. Yeah, you can take with the screen. And then that side. 一定到。
都有人慢慢听。
Yeah, thank you.
你看要帮这样讲好就那边。你们的 slide 放上去啊，我们 slide 放了一个 slide。哦，不要放一个 slide，那没关系。没。
Whose phone is this? London? Oh, I see now. Stood up. He isn't got stood up today.
Is it still recording? Shit.
I think it is. Don't worry. No one will get a break time. I didn't say that. He did.
Oh shit. Oops.
Okay. Oh. Okay.
Hello. 哦，他讲他下午才来，吃晚饭过程。他早上啊什么？哦，那他早上有 family 的事情。Yeah. How was the presentation? I think it
手写的东西。对啊，就是我有些会写，
because the
啊，有些东西，他就是有些东西我不是没有写，也想，然后
actually still there are
就是
still
那个
examples
两百个，然后问的话，
but I guess for this type of if you have a lot of definition that you want to do, I think your example is more important. I mean, when you go through the example, actually you have to go through the definition instead of you go through the definition. If
没有，这是5个人的，是5个人，
harder,
这是5个人，just check.
yeah, I mean harder to okay. So what do you mean? No, because if you show the definition and then we have to go through the definition, no, we have to imagine ourselves first. Instead of you straight away give us an example and ask from us to generalize the idea from this. Yeah. For your part. I think still fine. I think your part is still fine because I think your part is still fine. At least in sequence, but yeah. If there's I mean, you show some of the example, but it's not everything, right? Yeah. So if you could have a running example, then yeah, I think because you already show part of it already. Actually, so basically the simplification part. You make things into simplification, and then maybe it's good if you can directly show us on why after do this, and then we have some smooth kind of variety.
What is the time? What what's not enough?
Yeah, I mean, like if you wouldn't show that, maybe you don't want to like dwell too much on your statement. You should bring the statement or definition out. I mean, from explaining the example. Yeah. Or you can directly just jump into this example. Oh, that's why see there is
Jump in the example immediately.
because the purpose of definition is to serve the examples. Yeah. So if you want to do it formally, then take time or sometimes from the definition we want to capture what's important. I think but if your idea is really depending on the yeah. Oh, okay, that one would be I think after Monday on the revision class.
Revision.
Yeah, I will mention it again on
Next 2 weeks.
yeah. If another weekend to do.
Thank you.